exclusive OR with a carry in, and that should be our sum. Okay, and then what is our carry out? Well, it's our ands. Let's draw those. And there you go. It's basically this guy is A and B. And this guy, what is this one? Well, it's carry in ANDed with the exclusive OR of AB. And those guys are ORed together to give us our carry out. Okay, let's take it even one step further than that. Those exclusive ORs there. Let's pretend you go into the parts bin. There's no exclusive ORs. Well, you can do a sum of products of both the carry out and sum. So here's our carry outs. Those are the ones, and these are the ones for the sum. So let's do our Carnot maps. Let's do, which one do we want to do first? Let's do sum. Okay, so where is it one? You're just going to go ahead and map out where they're located. Right there. Looks like they can't be grouped in any way, shape, or form. So what are we going to get there? That one's not A, not B, C. This guy right here, that is not A, B, not C. What's this guy? Well, that's A, not B, not C. This guy, regular old A, B, C. Okay, and then so what does the sum look like? Well, it looks like the, geez, that's the worst sum ever. The sum is the ORed implementation of those products. So first one was A, not B, not C. We're going to add that to, Boolean add that to there, and then we've got, and finally we've got A, B, C. That's sum. Okay, let's do carry out. So carry out. And 1, 0, 0, 1. Where is it 1? Well, it's 1 here, here, here. So we can make 3 groups of 2 terms. That's BC. That's AC. You guys can stop the tape too and do this along with me too. So I'm just flying through this here. So carry out in this case is AB plus BC. Excuse me, A and B, or B and C, or A and C. I was getting all binary on you because we're still in Boolean zone. Okay, so now does this make sense up here? Does this expression right here, this is the sum of products of our sums and our carry outs there, does it make sense with what we've got here? Well, let's go ahead and let's just do carry out. Well, so carry in, we're talking about this term right there, carry in and exclusive OR A, B. So think about this. Remember we talked about earlier where our exclusive OR can be written as not A and B, or A and not B. So let's carry in, distribute that out, not A, oops, 1 second. Let's distribute this here. And let's move that over here, make it easier to read. Okay, so that's that first leg. Now the second leg right here is A and B. Okay, does that work with our with what we have right here? Where is it right here? Carry out there. Well, through a bunch of Boolean laws here, what you can do is, well, I don't want to do the whole thing, but basically it's, you can split this guy up. You know, and because of this right here, that can be simplified as just, whoop, 1 second here. A B plus Cn, and distribute that out. And yeah, do a bunch of those things. What you get is AB plus BC, excuse me, A and B, or B and C, or A and C. Same thing as that guy. Let's do the same thing for our sums. Remember our sums were, well, this is what we came up here with the sum of products there. And what we had was, well, let's write it down here. Keep that in mind. We're going to make sure that A or B, excuse me, A exclusive or B, exclusive ORed with C, is equal to what we came up with our sum of products there. So that exclusive OR can be redrawn like that. And let's just, and we can distribute, well, let's, so this right here. Now we can go ahead and basically break up this exclusive OR. So where it's C ORed with not C, oh, excuse me, not C, ORed with C, and that whole thing is negated right there. Okay, so that is, now we gotta go start breaking this down. This guy you can distribute, that's easy. This portion is easy. This one we gotta start breaking that down to using De Morgan's theorems. And basically what that's gonna look like is those guys are gonna be ANDed together. And now we're gonna have to break those down through De Morgan's theorems again. And then you FOIL through, and ad nauseum, you get this guy right here. Sum of products implementation of the sum, and the sum of products implementation of the carryout. Let's go finally finish up our full adders here. So why is the full adder so important? Basically, it allows us to do this right here, what we were talking about earlier, where this guy, this first column, is just got a carry-in of 0. It's an implied carry-in of 0. And this second column here has the carry-in from this column. So basically you can nest full adders if you think about this and do this is a 1 full adder, this is 2 full adders, 3 full adders, 4 full adders, on and on and on and on to however many bits you get. So if you've got a 16-bit number that you want to add together, basically you are interlinking full adders, okay? Which we're going to talk about in the next section, parallel binary adders.